Uh, Thanks for the nice introduction, and I'm very glad to be here. Today I'm going to talk about this kind of material, topological material. We talk about the waves in topological material. I will focus on the mathematical analysis and also propose some numerical methods since this is scientific computing. Uh, this is a joint work with my grad students at Tsinghua University. With Yin Cao, we together do the analysis part, and also my collaborator Hailong Guo from University of Melbourne, but he recently came back to China now, and my other collaborator Yang Xu from UCSB. Okay, so today I will talk about, this is the outline of my talk, and I will first give you some basic idea, knowledge on the what about topological material and the waves in topological material and the recent studies, and I will talk about the mathematical analysis part and some numerical part, and then do some concluding remarks. So every time I talk about topological material, I use this picture. So we know very famous honeycomb-based topological material. One famous example is what we call recent graphene. So basically, it's a single layer carbon atom in a 2D honeycomb structure. So due to extraordinary property, due to this kind of delicate structure, so the Nobel Prize just 15 years ago, and Jim and Novoselov got the Nobel Prize because they successfully made the graphene. And due to its success, people trying to use this kind of structure, delicate structure to do like photonics. They put like some kind of waveguide with this kind of honeycomb structure they put there, and they can get some analog phenomena, what we call photonic graphene or artificial graphene, not just in photonics, also in acoustic waves, and also mechanical waves, and a lot of other phenomena. So, what speciality of this kind of structure? I'll give you two examples. So, we know that this is a periodic structure when we study is kind of a dispersion surface or energy bands. We see there is a single direct cone here. This is called energy bands. The first and the second band, the two energy bands, they just touch each other at a single point, and nearby this is a cone. They call it the direct cone. And what about that? There are also a lot of very important property of the material corresponding to this kind of delicate structure. For example, so here I give another example. So we have two materials. There's some kind of a material. Basically, there is an interface, kind of an interface. The upper half is one material. The lower half is another material. The two materials glue together along this kind of curves. We call interface. Both the upper one, the lower one, you cannot tell the difference, but they have some kind of a difference. Just topologically distinct materials. So you glue them together. So what special thing can happen is that, so if you generate some kind of waves at the point 1, and the wave will propagate along the interface, even though there is some absence or defect, the wave are immune to this kind of defect or absence. So very robust. This is called robust wave motion. So this why? So we want to understand why. Of course, since we are doing mathematics, a lot of experiments and also physics, they have some kind of interpretation. We want to understand this phenomena. For example, how do you prove the existence of this kind of direct cones, or how do you prove what kind of wave of this propagating along this kind of interface? That's what we want to answer. Okay, give some earlier works. So ever since Wallis, the physicist, pioneer work, like just about 70 years ago, and he proved the existence of the direct points in the time bending model. And after that, numerous mathematical studies have been dedicated to this kind of honeycomb structure. So such as they do existence of direct points rigorously, mathematically prove that, and also study the wave dynamics and do some homogenization. So what's the kind of homogenized property of this material? And we do what about topological edge states? And in theoretical physics community, they talk about the bulk edge corresponds to how many edge states there are, or what about the property, and so on. So there are a lot of mathematics and applied and pure mathematicians. For example, Pfefferman, just Yao Zhigang, Professor Zhigang Yao just mentioned that, okay, or not others like Mary and Mike Weinstein, and also myself, I did some work on this community. Okay. Just talk about honeycomb. What about, my title is about the super-honeycomb. What's super-honeycomb? Okay, a new material, metal material, they put like 6 sides, this kind of like a honeycomb. They just regard this kind of a diamond region as a unit cell. They put 6 sides in one cell. If the 6 sides or six inclusions on very special positions, you just regard it as regular honeycomb. But if you shrink or dilate the 6 sides, you can create 2 topologically distinct bulks. For example, if you shrink like there are 6 sides, like 6 atoms, you just shrink the 6 atoms, or you dilate like 6 sides, then you create 2 materials, right? And for each one, for example, if the 6 sides are in very special positions, you can prove that there exists kind of not just a single cone, there are a double cone. That means 4 dispersion surfaces touch at each other, touch at their single points. This cone structure. That means 2 cones on top of each other. But if you dilate it or you shrink the material, okay, the 6 sides, you will open a gap. There's no gap open. You open a gap, and you just like honeycomb structures, you glue them together like 2 bulks. One is dilated, one is shrinked. You glue them together, you can get like 2 edge states. This red curve, you get 2 edge states, or I'll explain later. There's some kind of edge states. So, okay, good. Yeah. Something like that. I'll explain later. Okay. So, just you actually you didn't depend on how you define time reversal symmetry or parity symmetry, or I'll explain later. Okay. So good. At least we have some experts here. Okay. And originally this material was proposed by Professor Hu from Japan, and he used some time-bending model to mention that the two edge states, the energy curve, 2 edge states actually cross to each other. And later on, people do some careful study, like they found that the 2 edge curves, they don't cross. Actually, it's like there is a gap, or then we get 2 gapped branch of edge states. So, but both are from numerics. We want to understand mathematically. That's it. Whether this, whether that, or why is this and why is that? Okay. Okay. So the goal. So we are doing mathematics. So the goal, we consider general setup. We consider the elliptical operator, just the very, very general elliptical operator in R2, or defined in R2 space. Okay. So if rho equals 1 or A is identity, you get a Schrodinger operator. And also if the potential is 0, A is identity, you get Tm wave and you get Te wave in Fertility setup. Okay. So basically they are the same, but the length is almost the same, except you put some conditions, different conditions on rho, A, and V. So what we are going to do? The first thing, we want to obtain some essential mathematical characterization of this structure. For example, symmetries. What's the minimum requirements for these material weights like rho, A, V? And can you prove the existence of double dual cones and corresponding edge states? Or, as I said, there are two different physicist papers. One claims that the two branches across is like a spin. And the other one mentioned that the two branches actually there is a gap. Why? We want to understand. And also, since we are doing applied math, we want to propose efficient and reliable numerical method how to compute it. That's the standard applied math approach. So before that, we want to do super-honeycomb. So we want to do, first I want to explain what honeycomb. Honeycomb potential. So here, different people use honeycomb in different contexts. They mean different things. So mathematically, I use the Pfefferman's definition. Okay. So Pfefferman in 2012 and Pfefferman-Weinstein together, they just get some essential mathematical condition for the honeycomb. They define like first satisfy the parity symmetry. That means the V is even, and the time reverse symmetry. That means V is real. But here I didn't mention that. So for the mathematical analysis part, even though our analysis is applicable to the general elliptical operator, but for the analysis part, I just studied the Schrodinger operator because it's simple. But simple to explain the basic principles. So in the mathematical analysis part, I use the Schrodinger operator as an example. So we only have one material weight function like potential. So here we need V is C infinity, but it doesn't matter. In L infinity is possible. So just I don't want to. I just want to study the symmetry, so I don't want to pay a lot of attention on the regularity. So I just mentioned that we have a parity symmetry, we have time reverse symmetry. Also very important, we have a 2π/3 rotation symmetry. And together, of course, since we study both, it's periodic, so we have also add translation symmetry. We have a U1 translation symmetry. That means it's periodical along U1. Since it's also rotation symmetry, actually you have U1 is periodic, it's rotation invariant. So you must have another period. So you have RU1 is also periodic along U1, and RU1 is also periodic. So we can define the lattice. That means that actually the potential is translation symmetric along the lattice defined by the U1 and the RU1. They are independent. Okay, just give a very brief review on the periodic Schrodinger operator. So suppose consider the periodic Schrodinger V is periodic. You have two periods, like U1 and U2. They are independent. So we can define the unit cell, like unit cell, omega. And also we can define dual periods, like K1 and K2. We want to do some kind of transform, like spur transform. The the dual, they satisfy this condition. It's like a reciprocal condition. Also can define the dual unit cell, like a Brimzone is actually, Brimzone is a very special form of dual unit cell, but I don't want to make the difference. Okay. Is also, you can K1, K2, also generate some kinetics, and the unit cell is, we call omega star. So as I said, we can use the standard Floquet block theory that implies originally we want to study this operator, right? The Schrodinger operator. They defined in the definition. They defined in L2. You can like subspace in L2, R2, the full space. Define the operator, the function defined in L2 and 2 like L2 like H2, for example. So we want to study the spectrum of HV. We know that the spectrum of HV acting on L2 is actually can be decomposed into HV acting on this is a unbounded domain R2, but can be defined in a bounded domain omega. But you have to put some kind of a K parameter, they call the Floquet index or whatever, or quasi-momentum. K is defined in omega star. So that means here L2 K omega is you put quasi-periodic boundary conditions. Here, this kind of is a plane wave times the periodic part is satisfy some kind of quasi-periodic boundary condition. The quasi-periodicity is characterized by this K, so you call quasi-momentum. Okay, so originally you want to study the spectrum of HV, and you can study this kind of HV defined in this kind of quasi-periodic boundary condition L2K in a bounded domain. So we know that, and for each fixed K, actually, for each fixed K, we know that this is initial operator defined in a bounded domain, so the spectrum is discrete, right? The discrete spectrum. So for each K, you find a discrete value of EB, like we indexed by the B, the E0, E2, E0, E1, E2, E3, and go on. So, and goes to infinity. And also that for now you vary K, we can prove that EBK is Lipschitz continuous in K. So it's Lipschitz continuous. We cannot prove that it's analytical due to the degeneracy. Because two dispersion bands can touch each other at the touching points or touch regions, they are not analytical. So we can only prove it's Lipschitz continuous. So we call this fixed B and you vary K as a function of K. This called the Base energy or dispersion band. Okay, this is the energy band. So what we want to study? We want to characterize the energy or dispersion relation or energy bands. This is the key. The key is very important. A key feature in a lot of in condensed matter physics. They want to understand what's the energy band structure of one specific crystal materials. Okay, and okay, then what's the direct points or direct cones? As I said, we have dispersion band. What direct points is kind of a very special K and or special energy or ED or energy such that the dispersion bands or dispersion surface is kind of in the specific K star in the nearby is a cone. This definition, what kind of, I put a definition of direct cone. So for the Schrodinger operator with a honeycomb potential, I just defined a honeycomb potential. Pfefferman and Weinstein in the James paper, 2012, they proved kind of guarantees the existence of direct points. They only put 4 symmetries. Actually, 2, just like they only need 1, 2, 3, 4 symmetries. They can prove that there exist direct points. Okay, this is for the honeycomb structure. Okay, this is the Pfefferman, very pioneering work, like was 10 years ago. And then what about Super-Honeycomb? How do you Super-Honeycomb? How do you characterize Super-Honeycomb? So we characterize like this way. Okay, so Vx is Super-Honeycomb potential if additionally we satisfy 1, 2, 3, 4 as a honeycomb. But if additionally we call the folding symmetry, that means you have a V1 is translation invariant along V1. V1 is small, defined like this. It's actually the length of V1 is smaller. That means basically you treat it as a honeycomb potential. You have U1 and U2 satisfy this kind of symmetry. But if you treat it, you have a even smaller V1 translation invariant along or even smaller period, okay? Then we call this kind of folding symmetry. Due to the rotation symmetry, you have V1, you can also define V2 due to the rotation symmetry, okay? So we also put some kind of a technical assumption. That means it's non-degenerate. That means this non-degenerate condition. That means, okay, you can even put even smaller. Okay, this is not allowed, right? We want to just put a smaller. V1 is the smallest one. You cannot find an even smaller one. Okay, this is the non-degenerate condition. Okay. So sorry. The emergency of. Yes, sir. So I didn't get your.
No, the question is, should I be thinking of the Dirac cone as the emergence of a massless degree of freedom?
It's a massless Dirac system. Yes, sir. There is no mass. If you can gap, there is mass. Okay. This I give some this U1 and U2. I give some like examples, and you have V1 and V2 is smaller. That means it actually, even though it has a smaller periods, but we regard the material is periodical along U1 and U2. Why we do this? Because eventually we want to dilate it or shrink it. We if want to shrink it, if I dilate it, and it's no longer, that means we want to break the folding symmetry. There is no longer, we have to treat, we have to study the lattice along U1 and U2. Okay. Okay. Fourfold symmetry, as I just mentioned, that inspired the previous results, for example, numerical results and so on. We know that the fourfold degeneracy actually occurs at GAM points. So we want to actually study it, investigate. Oh, what about the dispersion property at the GAM point? Okay, we want to study. Consider eigenvalue problem. Okay, and this is our working space. Chi, since it's at GAM point is the k equals 0. So basically, chi is our working space is periodic function space. Basically, periodic function space. So just give some here. Chi is actually invariant along the conjugate, or you call the conjugate, or in the Schrodinger case is time reversal. Also the rotation symmetry, also is priority symmetry, also say is very the C chi is chi, R chi is chi, P chi is chi. Okay, it's the same. And also H is commutes with this kind of symmetry operator on chi, so it's very easy to verify. And due to the symmetry, we use some symmetry arguments. Our working space different from the Schrodinger, different honeycomb. The R symmetry is very important. Here, due to we have some kind of additional folding symmetry, we can decompose our working space chi like this one. We have this kind of space composition. We use this kind of symmetry operator to the eigenspace of symmetry operator to characterize the subspaces. That means chi can be decomposed into this kind of subspaces of the folding symmetry and rotation symmetry. Originally and we can prove some kind of property of these different subspaces. They have some kind of if you apply P operator, you come from one subspace to another subspace, and also for the rotation space, also for the conjugate operator, also the PC operator, and so on. Okay. Oh, okay. Then our first result is this. Consider this kind of Schrodinger operator. There is an epsilon, and with Vx being a super honeycomb potential I just defined before, we use 4 plus 1. 4 is honeycomb, and 1 is additional symmetry. And then we can prove that you can always find a folding four-fold eigenvalues of HX of this Schrodinger operator. This is Floquet-Bloquet eigenvalues. And you can always find the fourfold. And in the nearby, they are just in the nearby for the fourfold. There always exists a Fermi velocity such that in the nearby is a cone. That means there are 2 cones on top of each other, and the VF is exactly the same. That means 2 identical cones on top of each other. I'll explain later why this is true. Okay, this is the proof is the standard, not a standard. Okay, the proof we consider 3 steps. We just follow the Feferman-Weinstein's proof on the honeycomb, but since this is a little bit different, so we modify the proof. I don't get the details, but I just give some outlines. So first, we prove with some recurrent condition, the fourfold geometry can yield a double-zero cone. So we use the main technique. We use the Lyapunov Schmidt reduction, just perturbation theory, basically. And then we just divide the fourfold geometry and the required condition. I just mentioned that hold for epsilon is small. Here we have a parameter epsilon. That means for channel potential, we prove the existence, and then we extend the fourfold and the required condition hold for epsilon large with some kind of analytical operator theory. This is the standard way to do it. Okay, so I don't want to get details. Okay, I just don't get the physical model correct and band structure. So as I mentioned that what about super honeycomb? We add some kind of folding symmetry. What if you break the folding symmetry? For example, you shrink it or you dilate it. So we consider a perturbation. That means the Wx satisfies the original symmetry, but no longer satisfy this kind of additional folding symmetry. That means the V1, the smaller period, is no longer the period of the W, but it's still a period of V. That means you break the folding symmetry. And we have the perturbation. So that means, okay, basically it says, okay, I don't want to read it. Basically, it says as long as W is not very special, for example, non-zero condition satisfied, that means you always open gap. That means that. For example, originally they are, if satisfied the folding symmetry, they are in this part. This part is the shrinking, and this part, this figure, you dilate it, like extend or the material. And what else? This is original, unperturbed. The perturbed one way, the perturbed the other way, and you get open gap. This is local dispersion surface. That's it. Okay, the above analysis is about the bulk. What about what I said? What if you glue the 2 distinct? As I said, we have 2 ways to break the symmetry. So you glue them together. Okay, that means the mathematical model I used like this. You have a Schrodinger operator. So originally this you have the folding symmetry. super-honeycomb structure, you get a Wx is used to break the symmetry. And you also get the Moore function. The Moore function is eta. And we have parameter delta. Okay, delta is usually small for example. Okay, so here we have I2. That means we have a material here. We have a material there, and this is I2, and this is the interface. We have two. That means here plus means, for example, we means all the material. We expand all the 6 points. Here, when we shrink, but we didn't break the rotation symmetry. Okay. And this is I2 direction. As we need 2 here, that means if eta is the Moore function, that means take the value respectively. One way is +1, here is +1, here is -1. So far away from the interface, you have 2 limiting operator. We call the H plus minus delta. H plus, that means far away from the interface, you get a bulk, it's periodic bulk, and it's we call the plus and minus. Here we use a rational edge because our method we need is kind of a rational edge. That means we can put any direction, right? We can any direction glue them together, but we need at least I2 is perpendicular to some kind of lattice points or lattice vector in this lambda. Lambda is U1, U2 defined by the lattice. That means at least we need to along if there is W1 perpendicular to I2, that means along this direction, the material is still periodic. Otherwise, we don't have any periodicity. That means we have one periodicity along this direction, along the interface, but along perpendicular to this direction, we don't have any periodicity. That's because this plus this minus they are different. So that's it. And since we still have one periodicity, so we can still use Floquet block theory, right? So that means your operator originally defined in the full space, but we can break into a cylinder. In a cylinder, and K parallel is like a Floquet index or quasi-momentum, whatever we would call. That means it's quasi-periodical only along W1 direction and then along the interface direction, but no longer periodicity along that direction. So now these things are different. Why different? Because the unit cell omega E is no longer bounded. It's a cylinder. So that means you define an elliptical operator in elliptical is defined on unbounded domain. That means, okay, it's possible that it's not a discrete set anymore. It consists maybe continuous spectrum, usually, most of the part, and may have some kind of point spectrum. May or may not. It's possible. So the point spectrum will actually correspond to the so-called edge states because they are decay. They decay along that direction. That's what we want to prove. Whether you can find and for specific gap, how many you can find. This is the center of quantum metaphysics. This is called the bulk edge correspondence. Okay. But I'm doing some kind of analysis part, applied analysis. We don't want to go that deep to bulk edge correspondence. So our second result is that. So just study that operator. This operator, if delta is small enough, okay, if delta is small enough, we can actually prove that if delta is small enough, we can actually prove that the energy, you can always find some kind of energy E1 and is not E2 at a k parallel equals 0, you can always find the 2-point spectrum. We call E1 and E2. They are different. And corresponding states, we can characterize that use it's kind of a multi-scale characterization. It's decomposition of this phi 1, phi 2, phi 3, phi 4 are due to, if you unperturb it, we have 4-dimensional eigenspace at the point, right? It's a double cone. It's a superposition of this specific 4 points, but the envelope, alpha j is the envelope, but some correspondence, okay. This is okay. This is our first example. There's some kind of a combination, okay. And alpha 1, alpha 2, we have some specific specific decay modes. Okay, and they are anyway. I just want to show that they are just some kind of we can perturbatively find the modes and characterize exactly how the leading order behavior, the decay along that direction. Okay. The sketch of the proof. Okay. So basically, we do multi-scale. So we do multi-scale analysis. We expand the. Okay, well, hold me. We first observe the leading order of the eigenstates corresponding and the corresponding eigenvalue with multi-scale analysis. And then we transform the equation and to the remainder term. We want to estimate the remainder. That's it. You prove it. And the last two steps actually is pretty standard. The main part is how do you obtain the leading behavior. Okay, since how many times? 25. So I want to give a very brief matrix expansion. So basically, we want to start this eigenvalue problem, and we already know. So we expand the energy. S is basically the k parallel. Basically the k parallel. S is the small parameter, basically the k parallel. So we want to expand as delta in terms of delta order 1, delta to the delta 0, delta 1, delta 2. And also we expand the eigenfunction, the standard multiscale, and do standard multiscale, and use kind of solvability condition. And if we use solvability condition, we get a leading order. We get what we call the effective drag. So what you mentioned that we get is here. Oh, okay. Or mention that it's not just a massless direct due to we have a domain wall. The domain wall that plays the role like mass term, something like the mass term in here. It's a mass varying. You know, domain wall is plus and minus or minus plus. So it's like a mass varying direct. So to leading order is a mass varying direct. And since our problem later on we need we can even solve to higher order. Due to original problem, we need to actually go to higher order, because in higher order we can have this gap opening. So we need to go to higher order standard way. So this is pretty long. So I don't want to show the details. Then you go standard multi-scale analysis. You go to higher order, use solution. You get some kind of bifurcation of two. That means two leading order. The two edge states together, but to next order, you can see they just separate to each other. That's our results. Okay, so I give since this is a mathematical analysis part, so I give a brief conclusion. So for the analysis part, for the super-honeycomb material, we first introduce what we call the folding symmetry to characterize the super-honeycomb material. And compared to the original definition from Fepperman and Weinstein in the James paper. And then we prove that, and if the folding symmetry holds, you can find 4 folding, that means 2 direct cones. If you break the folding symmetry, the break cone just break. At that point, you don't have this kind of, you introduce mass actually, but still periodic case. And this is the main conclusion. Also, we glue them together. We find, if under probatively, we find the existence of edge states. Two leading order, they just together, but to higher order, they separate. That means, originally said, okay, in the 2 physical papers, originally they thought they just cross to each other. This is not true for the continuous version. But this is true. That means there is gap, or even gap. If the perturbation is very small, the gap is very small. It's to the order delta square. But why they plot figure like this? I asked the author. Actually, they use the type binding model to plot the figure. For the tight binding model, it's true. It's like 2 dispersion curves, energy curves, they cross to each other. For type binding model in this case, okay. Say again.
While semi-metals.
Oh, while.
Yeah, while.
But while semi-metal is 3-dimensional, right?
Yeah, but if they separate.
About if they separate, you get whiles. I don't know. I didn't go that direction. Okay, sorry. We can decide later. Okay. So then we clarified why this is true. Okay. Now, basically, the mathematical analysis part is basically understand that from mathematical point of view, we just studied the spectral of some integral operator in some kind of with some kind of structures. Okay, symmetries. Now we do numerical part. Okay, numerical methods. How do we compute this one? So standard we usually, for example, periodic part for bulk part. In the literature, people like use some kind of spectral method. They use Fourier transform. Fourier transform is periodic, right? You can expand everything in Fourier series and to do it. But it's good. It's very fast, efficient. But in real applications, the material weight is not C infinity anymore. It's actually piecewise constant. So if you do Fourier transform, there will be some accuracy. There was some problem over there. So here, for example, we take this kind of divergence form as one example. So basically, for example, we want to study this divergence form integral operator. Define original, for example, this eigenvalue problem is a cylinder. That means we want to study the edge states. How do you compute it? This is a cylinder. If delta equals 0, this is for the bulk case. You want to study the energy surf. But for that one, if you want to study the edge states curve, so the eigenvalue problem we do kind of introduce the periodicity we do this kind of block transform. We put in a periodic part, some kind of a periodic boundary condition, and we use this form to use to propose our numerical method. We use the standard finite element to compute it, the standard variation formula to get the binary form. This is very standard. This is a standard way to compute with the finite element. But what's not standard, as we already know that for standard linear finite element approximation, you can find the eigenvalue the accuracy for the eigenvalue is the CH squared. But the eigenfunction, if you 0 norm, okay, L2 norm is CH squared, but 1 norm is CH. That's standard linear, standard finite element, linear finite element. But you found, what if we want to go higher order? For example, why we want to do this? Because in the Maxwell setup, in the photonic setup, some kind of gradient. This is the gradient norm. Okay, the gradient of p or the eigenfunction. The p and the gradient p, they some kind of appear together. But if you use the standard finite element, they have different accuracy. So we want to put some kind of, we want to do some kind of posterior operations to improve the accuracy, even use linear finite element method. So what we used, we call the polynomial preserving recovery operator. We use the posterior operation to get, we call the gradient recovery method. We do some kind of, for the eigenvalues, we bring some together, like put some information of the gradient of your numerical eigenfunction. You find the numerical function gradient part. We put some kind of way to do it, to recover the eigenfunction. And after that, we can get our eigenvalues to accuracy to CHQ. But actually, our numerical shows is 2h to the fourth. But we cannot prove it. But this is not sharp estimate, but we can do it to CHQ. And the eigenfunction, the eigenfunction, the gradient, the accuracy of the gradient is to improve to h squared. Okay, this is the, we call this superconvergent post processing. This is our numerical test, and the standard linear element, linear finite element, standard element, linear element, we get this kind of second order accuracy, but for our way to do it, we get a fourth order. This is for the smooth. What if for in real application the material weight? For example, in photonics, as I showed in my first slide, they are not smooth. The material weights are not smooth. Actually, they are piecewise constant. For example, for here, inclusion, inside the inclusion, you have one value. Outside the inclusion is another value, and the G could be very big. That means high contrast. For high contrast material, we propose this, what we call unfitted niches method. So it's not a body fitted mesh. Because generating body fitted, you along this kind of interface, you generate some kind of a mesh. It's very time costly, and for very complex geometries, it's very hard to, and it's totally non-trivial. So we use unfitted mesh. It doesn't matter. We don't care. We use the standard because the unit cell, for example, the unit cell is like this way. It's very easy to generate the mesh, but we have some regions like the mesh region, and there is no mesh inside or outside the interface. And we put some kind of this. No, I don't want to go to the details. We just put some penalty function at the interface. That's it. With the niche, the variation formula to put some penalties here. Lambda is parameter, and we can still get the eigenfunction. See, suitable condition. Okay, the eigenvalue, the accuracy is CH squared, and the eigenfunction is also CH squared. The zero norm. Okay, because we don't do any posterior processing. Okay, but still second order accuracy. All right. And also compared to spectrum method, For no contrast, spectral method still can get some kind of accuracy. This we studied the honeycomb case. For example, for no contrast, the spectral method still can get some result, but our method is much accurate because this is for the direct case, direct point. This is for open gap. But for high contrast, very high contrast, we still get a very accurate result. But Fourier method was Fourier method does not give you any accurate result. We know that there is a direct point here, but here we get nothing. So that means our method is suitable for high contrast materials. This is for the dispersion curve. Also, I give some other results. For example, for Schrödinger operator. Okay, sorry. There is. Okay, for Schrödinger for super honeycomb potentials, we still get like direct points with very accurate and open gap. Open gap. If you decompose the perturbation, you open gap. This is for smooth case, and if you for photonic setup, it's the same. Inside the inclusion, there's some kind of weight. Outside is another material. Okay. This is for bulk. If the standard superhoneycomb case, if you shrink, if you dilate, you get fourfold. You bring mass, right? As you mentioned, you bring mass, you open gaps. And if you put two material together, this is shrink, this dilate, the plus, minus, the interface. You can get two interface mode. One is that, the other is that, or from here, one is from, and dispersion curve is exactly like that. So there is a gap. You get two gapped branches of edge space. Okay, I think I'll give some kind of a summary, summarize this talk. Okay, basically I have two parts. One is the mathematical analysis, the other is the numerical methods. So I didn't go to the details. The first, we get some essential mathematical ingredients. How do you characterize what we call the super honeycomb? So we add folding symmetry. So, and we prove the existence of a double direct cone, and also existence of two gapped, not cross, two gapped branches of edge space, at least in our setup. And we also prove some numerical method. If the material weight is very smooth, if you want to improve your accuracy, even use linear elements, you can use the gradient recovery method, what we propose. If for the discontinuous material weight, you can use unfitted niche. And they are both elements, finite elements methods. Okay. Future work. So since we didn't, even though I call this a topological protected, but I don't have any time on the topological interpretation. What about the chain number, chain index, and so on? And I didn't talk anything about the dynamic property of such indices. We only suppose the interface is straight line. You can find the edge space. What about this? The interface is curved. What's the property of this edge space? Still very robust, and so on. And as I said, I always assume that there is I2 must perpendicular to some kind of net vector, but that means we need the interface is along is periodic. The material is periodic along the interface direction. But what if we call this irrational edge? What about incommensurate? That means it's irrational. We don't have any mathematical tool to do the analysis. We think it's true, but we don't know. And also numerical methods about the dynamics. I didn't have. We haven't done this part yet. Okay. Okay, I think That's it. That's what I want to talk.
Oh, great. Before I proceed to the question session, I would be glad to say first welcome to our president, Professor Yao. Welcome, Prof. And then next, I will open the stage for you to ask a question for Professor Iju. Any question, please? Questions? Okay.
So regarding the existence of two-gapped branch of edge states, so do you prove this result for all the rational edges or for some rational edges, the existence of two-gapped edge states? So is that correct for all rational edges or okay?
Yeah, for all rational edge.
Okay, my another question is about the failure of the spectral method when you do the comparison. So the reason that why the spectral method failed is it because the spectral method you use doesn't capture this the interface, the discontinuities along the interface.
Yes.
Okay.
If the contrast is small, you still the Fourier transform still can give you acceptable results. But if the contrast is very big, right? Large contrast or high contrast. So you know the Gauss phenomenon.
Yeah. So I suppose the spectral method you use is somehow for the grid is for the whole domain, right? It's nothing related to the interface, right?
No.
Oh, okay, I see.
But we can use some kind of spectral element, some kind of other elements, spectral elements. It's still, but we use the Fourier elements. Okay.
I see.
Thanks for the talk. Can you turn to the page where there is a solvability condition on the opening up of the Dirac cones?
Okay. Yeah.
Yes, there's a solvable condition or something like that.
Yeah.
I remember there's a long equation on this solvability condition, and can you give some physical interpretation on this solvability condition, or is it just a mild mathematical?
Okay. Why this is true, right?
Okay.
Why can you need this one? Because you do eigenvalue problem, you do standard multi-scale analysis or standard perturbation theory. You assume you put this ansatz, right? You put this ansatz. You suppose you can expand your energy or in eigenvalue and eigenfunction in terms of delta q delta squared q delta to the fourth and so on, and you plug it into this ansatz. You could get linear order is the standard to the unperturbed operator. Because phi naught, we know that ED is eigenvalue and this is eigenfunction. So phi naught must be the superposition of four. It's a four-dimensional superposition of four eigenstates, right? Because it's purely periodic.
Yes.
But since we know that phi naught is also a function of this kind of a multi-scale or a slow scale, so they are the envelope. They call the envelope. And then you plug into, and you also get order one equation, right? Order one equation is no longer homogeneous anymore. It's inhomogeneous, right? You have some kind of right hand side part. So you want to also this operator is just this operator. Okay, this operator. So the kernel space. So in order phi one exists, that means the right hand side must be self-joint. The right hand side must be perpendicular to the kernel space. This is the solvability condition.
Is there any case that this separation of multi-scales may fail?
Yes. So, okay, for this setup, okay, what's the operator? For our setup, we have two. We put two delta here.
Yes.
If you remove either one, multi-scale method does not work.
Oh, so it depends on detail that how you add this defect into your
Yeah,
Hamiltonian.
the reason is that, okay, if you remove this one, that means to needle order is no longer this kind of Schrödinger operator. It's already, your perturbation means already in this is called WKB regime.
Yes.
It's really hard for this singular WKB regime. It's really hard. If you put here, that means you don't have two scales.
Yes.
You only have or we call perturbation or operator, but you don't have two scales. You only have one scale.
Okay.
So we need a two scale and small.
Okay, thanks.
Yeah, can you go back to, I don't know, one or two slides back where the delta W appears?
Which one?
Maybe even a little bit further back. But when you're doing the perturbation of the delta
Here?
W, no, it's earlier before
Oh,
you.
okay. For the bulk, right?
Yeah, that's all.
Okay.
Right. So here, I was a little bit confused because here you're assuming that delta W still respects the basic honeycomb structure.
Yes.
But
But okay. Well, I understand your question. Okay, you go
you already
ahead.
understand it.
Okay. So I'm not sure if I understand correctly. So you want to say if W is honeycomb, this is super honeycomb, but together it's honeycomb, right? So honeycomb, we know honeycomb has the direct points, but what about the direct points? Where the direct points are, right? So CR, okay, I will plot a figure, okay. So basically, what we care about, okay, here, if you put dysregulation here, we open gap, but this is for gun point. That means zeros. Zeros. But somewhere else, we know for direct points in honeycomb is at not at zero, is at k and k prime. I'm not sure you know it. Somewhere here, we have direct point here. We have direct points right there.
So that point survives.
Survive,
So-
but it's
so-
twofold.
Right. There's a related question about the numerical calculations. I mean, I realize it's not. But if the way the numerics is done, there's noise that breaks the honeycomb symmetry, then you're going to see, for example, a gap where there really should be a Dirac. They have to be sure when they're doing the numerics, that respecting the translation symmetry exactly. Otherwise, I mean, the noise, the numerical noise in the simulation can act like something that breaks the honeycomb symmetry.
That's a good point. I'm not sure I really answer your question. So, for example, you don't actually know this is really a direct point or not due to the numerics, right? Yeah.
Have to do your numerics in a way that respects the honeycomb symmetry exactly. If you
Yes,
want to-
yes.
yeah.
Yes, exactly. But still, even do that, because we solve argument probably still you want your discretized the matrix satisfy same symmetries. Yeah, that's the reason still, but it's really hard. Even though, but we cannot let the matrix satisfy this kind of condition 100%, right? It's still some numerical errors. So that means for the double degeneracy here, still have some 10 to like 10 to minus 10 or 10 to minus 7, some kind of error. You see what I'm saying?
Yeah. So gap, what pseudo gap is being generated by the points.
Yeah. So, but we yes, a good point. We use very highly accurate numerics. So that means the mesh size very small and so on.
Okay.
Thanks for your nice talk. Actually, I'm not a mathematician.
Okay,
but
good,
I
good.
see a universality in particle physics when we are studying the Lorentz invariant in the system. I guess you have also something like that, the Dirac equation or the action, which is Lorentz invariant. Then in that case, we have this fourfold degeneracy. And by adding a new term, which breaks time reversality or parity, you can separate those
Yes, yes.
states. In that case, we expect something like two different light cones. But here you have the gap, but maybe that's because of this kind of perturbation that you chose. I'm not sure.
Yeah. Because
But yeah.
we chose specific perturbation to break some specific symmetries.
Yeah, this similarity, I don't know, but you are using this honeycomb and interface, but what I'm taking is just general action with Lorentz similarity. This is naive comparison. I don't know if there is any relation.
Yeah, in math physics literature, yeah, people use some kind of similar like Planar group and other action to study this problem. We use some, because I'm a applied mathematician, I use kind of applied analysis. So we do perturbation. So I think it, what I'm not sure if I know. So they need to probably same answer.
But this H that here is something like Hamiltonian.
Yeah, of course.
Then this is not Lorentz invariant. It's Schrödinger symmetry.
Second,
It is-
what symmetry?
It is Schrödinger symmetry. I mean,
Schrödinger
it's non-relativist.
Yeah, Schrödinger.
Okay.
Yes,
we will
Schrödinger
discuss
is
later.
not relativistic. Yeah.
Okay. Before we end, any more question, please? Okay, maybe let me ask one more question on slide 29. So how did you solve the equation 5 over there, and how many solutions does it have?
Which page?
Yeah, slide 29. Yeah. Yes, this one.
Okay, just so basically here the same. Okay,
Yeah.
so here you go to
Oh.
next order. This is the we have a curve space, right? We have curve space. The curve space is four-dimensional. Is four-dimensional curve, right? Curve is four-dimensional. So this what's self-joint? You want this. You get a non-trivial is solvable, means there is a solution. Right hand side must perpendicular to orthogonal to the curve. This give you
Thank you.
solving condition. And this meaning have a very long calculation you reduce to this. And you get basically this tell you, oh, okay. This basically tell you, oh, the energy of the edge states of the two states to that order, they are different. Okay, well, but basically
All right,
that's
all right.
the.
Okay, if there is no more question, we'd like to end. So let's thank all the speakers once again, please.